Hello friends, welcome back to my channel, a physicist Buddhist in California, and I am Sanjay. So today I'm going to talk in detail about a book that I mentioned in my previous lecture briefly. So this is a classic book on quantum theory of radiation by Walter Heitler. So I hope you can see the title of the book. So this is considered to be one of the most important books in quantum field theory before the modern version of quantum field theory was discovered, which was back in the 1940s. So Walter Heitler, who was a German physicist who worked mostly in Switzerland, he wrote this book back in the 1930s, and he basically managed to put the whole subject of quantum field theory in one book, and he presented it in a beautiful way so people could learn who wanted to enter this field. And of course, like I said, this was before the modern version of quantum field theory was discovered back in the late 40s by Schwinger, Feynman, and Tomonaga, the Japanese physicist. Schwinger and Feynman were American physicists. So we are going to talk about this book today. So in this book, Heitler laid out the whole view and vision of quantum field theory, what quantum field theory is supposed to be, and how one goes about learning it and doing calculations. So there are, like I have talked about in earlier books, and most of the examples that are directly relevant to us, especially for electromagnetic force, which is the force that we are most familiar with. Light is an example, of course. So it's all around us. That's what keeps the atoms together, binds the electrons to the nucleus, and binds atoms to atoms, and makes molecules, and finally makes life possible, including the solids and the liquids and the gases we see around. So the electromagnetic force has two basic components. One is the radiation or the photon, and the other is the matter, which is electron. So matter plus radiation is the quantum field theory of electromagnetic force that we are interested in learning about. So this book lays out the whole view, how this theory would basically be set up and how one would go about solving the problem. So that's what Heitler does. He starts with the radiation. That's why the book is called the quantum theory of radiation. But of course, he covers the matter part also. So it's, even though the title of the book may lead one to believe that he talks only about the radiation, but it's not true. He covers both parts, the radiation and the matter, but of course he starts with the radiation. So he starts and lays out how, starting with the classical electromagnetic field, one quantizes it to obtain a quantum theory of quantum field of radiation. So this quantum field of radiation then leads to the generation of the particles of the light that we know as photons. So each photon is an excitation of this quantum field of radiation. And then he does the same thing with the electron also. So there is a quantum electron field which pervades the whole universe, and each electron is a quantized excitation of that quantum field. So we have an electron field giving rise to electron, we have a photon field or a radiation field giving rise to photons, and of course the third part, of course, is the interaction between an electron and a photon, which is where everything has to come together. And this is what the book talks about. So what happened is that in 1920s, late 20s and 1930s, people figured out how to handle these two fields separately, the radiation field and the matter field. But the problem appeared when you try to take into account the interaction between the radiation field and the matter field, and there the theory basically blows up. It gives these nonsensical values. Basically the theory gives infinite values. So any theory of nature has to give a finite value for any physical quantity that one is interested in. So if it starts giving infinite quantities, that means the theory there is something wrong with it. In fact, in physics, we call such a theory sick. So a theory is sick, like a patient is sick. And people used to believe that the sickness is fatal, which means the theory would not lead to any kind of resolution, and this is doomed. But in the 1940s, these three physicists, Tominaga, Feynman, and Schwinger, managed to figure out how to resolve the problem, and so that's what is known as renormalization, which I talked about in the earlier lecture. So renormalization is the process, the mathematical process that the physicists discovered to remove the infinities that plagued the theory when one brings into account the interaction between the quantum field of radiation and the quantum field of matter, or in other words, a photon interacting with an electron. So basically, when Heitler wrote this book, that was the situation, but he covers the whole situation very beautifully. He describes how one calculates the quantities using a method known as perturbation theory. So how to calculate the terms in the theory by using the perturbation theory. Mostly one just calculates the first two terms. It's an infinite series. The perturbation series has infinite number of terms, but for all practical purposes, one needs to calculate the first two terms. Now, incidentally, and this is interesting, the first term of this perturbation theory can be calculated by the old theory. It's the second term that's where the problem appears. And so this is what this book covers. It shows the whole methodology, the process, the mathematics, how to calculate, how to set up the calculations. And then when you get to the second term in the perturbation theory, where things kind of blow up and one needs renormalization. So but this book that I'm holding in my hand is not the first edition that came out in 1930s. It's the third edition, which came out in 1950s. So by then, the renormalization program had been discovered, and so Heitler came up with a new edition where he talks about how this problem was resolved. He doesn't go into details like how the calculations are actually done using Feynman diagrams. For that, one has to look at other books like the book of Peskin and Schroeder that I reviewed a few months back, or Anthony Z's book, or Matthew Schwartz's book. So those books they basically cover these ideas. So in a way, we could say that there is a distinction between a classical quantum field theory and a modern version of quantum field theory. There's a mix-up of a term here, means of course. So the pre-modern quantum field theory had these problems which are outlined in this book, and these problems were fully resolved to a great deal of accuracy by the modern version of quantum field theory. In fact, the most accurate calculations in all of science, without exception, are in the modern quantum field theory of radiation and matter, which is known as renormalizable quantum electrodynamics. So the calculations that have been done by physicists over the last 75 years in the modern version of quantum electrodynamics are by far the most accurate calculations, and they have been these are not just calculations, they have been checked by experiments. So, and this is, I have talked about this earlier also, so I would mention that in the passing, that the calculations and the experimental results match to a great deal of accuracy, far better than any other field of science. In fact, they match to 12 significant figures. So it is an amazing degree of this match that happens between the theory and the experiment for renormalizable quantum electrodynamics. So I would end my lecture here, and so people who are interested in a bit of a history of quantum field theory should definitely look at this book. And it's not just the historical interest. This book is also quite famous because he actually shows how to calculate these really complex integrals. Of course, nowadays nobody does that by hand, they are all done by computers, but once upon a time people had to solve those integrals by hand. So if you are interested from that point of view, how these multidimensional integrals in 4 dimensions, how these integrals were handled, then absolutely this book is indispensable for that. So I would end the lecture here. I hope you found it informative and interesting. If you have any questions, please put that in the comment box. Thank you for your attention.